So let's get started for this week 7. Week 7, we will be on the feedback loop, appendix feedback loop, dynamic systems modeling. So lecture 13, dynamic system modeling. The objective is to introduction to the dynamic system modeling and solve differential equation by ODE, ordinary differential equation, INT integrator, okay, ODE INT. And balance equation, linearization, first order equation, time delay, and then FOPDT, graphic fit optimization. These different things that related to dynamic system. And we also have Laplace transform transfer function services, okay? But today we definitely not able to finish so many topics. So I'm trying my best to be simple and then talk about the core idea and get you started to simulate some dynamic system, okay? Time-based dynamic system. And we do have a video for the lecture last year, so you can look at it if you need to look at what's the content for this appendix, okay? But here we focus on coding portion, okay? So dynamic system. We have static system, we have dynamic system. So dynamic system means that you have some update, or you may have some time-dependent information, keep changing your system. That's called dynamic system. And you may have closed loop or open loop for the control. And these models are either derived from data, empirical data, so that is machine learning, right? Machine learning is deriving the equation from data and use the past data to build your system, system model, okay? So that one is empirical. Empirical means that doing a lot of experiment. And you can be physics-based using the functions to derive it, using the knowledge of you have to deal with the process. And combination of the two is often used in practice where the form of equation are developed from fundamental balance equation, okay, whatever. These are actually some topic to combine them, okay? So dynamic system, there are 4 common balance equation from conservation principle, including mass conservation, momentum conservation, energy conservation, and species conservation. This we call it balance equation, okay? So these are basic physics equations. And we can use input to build empirical dynamic system, first order, second order, okay? And we have the charge conservation equation, mass conservation equation, mass momentum conservation equation, whatever. These are several equations. We definitely not trying these. These are not related to robot. We may use some idea, but not going to use them directly. So step in dynamic modeling. The following general guideline for developing a dynamic model, the process is iterative and simulation result help the modeling. So you have some assumption, and during your development of your system, you need to go back to tune your model. And now, go back to the fundamental part. What are the models that we are trying to build here as dynamic system for robot? Okay, let's go back a little bit. It's over here. We have basically we have dynamic system. Okay, let's look at this one. Dynamic system. Not this one, okay? Not this one. Let me try another one. Okay, I think it's inverse differential, this one, okay? Okay, anyway, we do calculate Jacobian, whatever, a lot of things. And then we try to develop the first order equations. We try to have the open loop solution and closed loop solution. So closed loop solution is you use the Jacobian, inverse of the Jacobian, and you try to use a dynamic feedback system to tune your Q. And then when your error approaching zero, this is dynamic system. This actually is dynamic one. The one we have, that's open loop, okay, this so-called Scala manipulator modeling using the Jacobian metric. You come from some XY, you get Q, you get theta. These are state, these are open loop. Open loop means you give me the XY number, and I'm going to give you the function f. I'll get Q1, Q2 for you. And these are static because there's no feedback loop. No feedback loop means that over the time, system characteristic will not be changed. But closed loop solution is different. Closed loop solution is like you're based on the past data or plain data, and then try to tune your control. And you also get the input from the sensor. And gradually you build your system to find a stable solution. So this one is what? You build a feedback loop, and feedback loop tend to be dynamic system. And then you tune several rounds until you go to a stable state. So first you need to build this feedback loop and then model this feedback loop in real time. And that is the software simulation that we want to achieve. The step that we build the dynamic system modeling and try to make it simulate can be wrong, okay? Can be wrong. So that is our dynamic modeling. And we need to, these are the different steps, okay? So first you need to identify the objective of the simulation. For example, the simulation is to simulate the room temperature, okay? And we use the AC control. So that is the objective. And then we draw a schematic diagram. The input is the in-house temperature sensor, okay? And then the output is the control, okay, voltage or something. That is the schematic diagram. But in the middle, we may have leaking air, we may have some turbulation, we may have some noise changing our system, okay? Some door may be open. So those assumptions need to be listed down. And then we determine to use partial differential equation, PDE, or ordinary differential equation, and write the dynamic balance, okay, mass species. So using the dynamic balance, you can form the equation. And then you have other thermal reaction or geometrical properties. And then degree of freedom, you can calculate the degree of freedom and classify the input and classify the output to see which one is free value constant, which one is turbulence, which one is manipulated control variables. I'm sorry, the manipulated variable as the input. And output, look at the state, control system state, that usually is the control variable, the joint control variable, and the control variable. So these are the steps, and then simplify the equation, okay, and then simulate the steady state assumption, and then simulate the output, okay, simulate the output. Okay, so here case study, okay, case study. For case study, we do have a water tank, okay, water tank. So water tank has an outlet, okay, an outlet. So basically, we consider cylindrical tank with no outlet flow and adjustable inlet flow. So some input only, there's no output. Okay, so the objective of this exercise is to develop a model that can maintain a certain water level. Okay, so it's called P only control, proportional only control. Okay. Okay, so your DMDT, your mass change, okay, your mass change will be your inflow minus the outflow. Okay, this is conservation equation. So that forms the system that we have. Okay, so the assumption of a term in the differential equation DMDT, we get this one. Okay, so after that we use the rho is the density, A is the area. Okay, so V equals H. H is height times A. Okay, and V times density, the row density. You got the so-called mass. You got a so-called mass. So dBdt can be changed to such things. Okay, and your input is such constant rate of this constant rate. So you get such an equation. dH is the change of the height, change of the water tank height. Okay, original is change of the volume, change of the mass, then change of volume, and then change of the height. So change of height used to represent the proportion, okay, the portion of the change of the mass. Okay, and it's constant ratio to some velocity. That velocity is okay, the rate. The rate is the in-field rate. Okay, that's called U, something like that. Okay, so that we got that. Then we can simulate this simple problem. So we can derive the ODE. So ODE would be H prime equals H plus DH dt times delta t. This one is the so-called Euler formula. Euler formula is we have a curve. We do have delta t. We do have H over here. We try to measure this point H of x plus t delta t over t plus delta t. Okay, that's the point we want to estimate. So there is a tangent slope. It's a tangent slope times t delta t. You gotta change the height. Okay, so this is the equation we want to have. And dH dt, we try to calculate dH dt, and we actually the U will be 1 over S. Okay, this if we change to Laplace transform, we will get this. Okay, and step size is 0 to 0.1 step size. So this one is actually a open loop, no feedback. Okay, open loop, no feedback. So we can write a code like this one. We do have a time, so time series 0 to 10 seconds, and 101 points. So every 0.1 second, we got a point. And the C that's assumed is 50 kilogram per second. Okay, and U assuming it's zeros. Okay, zeros. Okay, at 101 point. Now the U value mu is over the time, the velocity of the velocity. So we set the 21 to 70 to be 100 at this time. So U is a function step, step function. U is a step function that from 21 to 70, it jumped to 100, 100. Okay, 100. Okay, maybe it's actually inch. Okay, inch per second. So something like that. Okay. Okay, so that is my U. I fill it in. Okay, that's the inflow speed. Okay, and now I need to sub the H. Okay, you have the U is inflow speed. You want to sub the H. So there is a tank. So tank level will be rho and A. So D that level is H. dH dt equals this. So wow, okay, wow, okay, so here we have dH dt, so that one is the dH dt, okay, and we do have the variable. I think the variable is H, okay. So we are trying to get the dH dt, D level dt, okay. That's actually by using this one, using the equation here, okay. By using the equation there. Go back, I'm sorry. Using this one, okay. So basically, we are trying to get the data, okay. So our H prime equals H plus dH dt times delta t. Okay, so this one we know. This one is actually equals Cu over rho A, okay. So H prime equals H prime minus H will be equal CU over rho A, okay, times theta T. Theta T is the interval, okay. So that is the equation. That is the equation. So let's go back here. That's the equation. So I have C divided by rho A. Okay, C divided by rho A will be the constant C divided by rho A. This is a constant. Okay. And then this delta T move to here. Okay. And this will become dH dt. Okay. It's become dH dt. Okay. This is actually delta H over delta T. Okay. So it's dH dt. So actually your D level dt will be equals C. Okay. I'm sorry, C here. Okay. And then over rho A, and then your valve is the U. Okay, valve is the U. So that's the valve speed. Okay, so that's the valve speed we have. So we can find the tank's dH dt. We can find the tank's dH dt. With inflow, we get a dH dt. So using the dH dt, okay, using the dH dt that we get, okay. So from 1 to 100, we have the U, okay, that's a valve level, okay, that's a valve level. And when we have the level 0, we use a 10. 10 is a function, so 10 actually is the dH dt, okay. And level 0 is H naught, okay, H naught. And then the interval is 0 to 0.1, okay. So that actually is the time delta T, okay, delta T. And the argument we pass the CV, so argument pass the tank function. Okay, so by doing that, we use the U minus 1, Y minus 1. Okay, so we use the Y minus 1. We use the Y minus 1. So Y from where? Y equals U0 or Y minus 1. Y is a sequence. Okay, Y is a sequence. So we use the previous one's value. We assign it to the level 0. Okay. So we pick up the level 0. Okay, we pick up the level 0. And level 0 actually assigned to G plus 1. Okay, so this one will be used for the. So basically, we are doing integral, right? We're doing integral. So we got the H. We got the so-called H0. That's the level 0. Okay, so level 0, we try to find H1. And this H1 still be called level 0. Okay, so we keep doing that. The G will accumulate your H0, H1, H2, H3. This is 1. Okay. So you will collect, G will get the whole thing, or everything you need to for your equation. Okay. So there are two constant. So it's a level. Level is the value to be integral. Okay, so that's the H value to be integral. And then time. Time is the times interval. Okay, time interval. Delta T. Okay, so delta T, the length of the time. Okay, the length of the time. And in fact, we do not use it. Okay, in fact, we do not use it. Anyway, level and this actually we do not use it. Okay, let's see. The tank, and we pass level 0 and 0.1. Okay, these are the two level 0, and these two are the level and the time that being passed to there. Okay, and then C and V are the two arguments. Okay, C and V are the two arguments. Okay, so by doing that, let's look at the code, okay? So this one is in water.py. Okay, let's look at it. Let's see now here. So here we're looking at let's see, color space, object location, PI controller. Let's see if it is this one. Not this one. Okay, not this one. Let me try another one. So here, lecture. Oh, no, let me go back to robot course. Okay, PT. Here, actually, okay, I think it's lecture 12, this one. Okay, so right here, we got the so-called water. So water is here. Okay, so the water is here. Water that text, okay, that's it. Water is here. So this is a water function. So that we have the level and the time and CV, okay. So that's wrong, okay. Okay, one moment, it still takes some time. It's running ODE and my machine is not super strong, but it's calm the data, okay. It's calm the data. Let's assume that this actually the so-called DUDT that is the inflow, right? And time constant. So this one is the changeable mass, right? So during this up period, you are infill data something into a system. So that's what we can get over there. Okay, so it's an integral problem. It is an integral problem, okay, over time. Okay, it's an integral problem over time. So we, from the side piece integral, we import the ODE INT, okay, ordinary differential equation. So here we start with the current I's value, okay. We use the Y minus 1. Y actually is the ODE result, okay. So we get the from U0 we not use, we started from U1, okay. So we saw that it's my bulb level, okay, to it. And then the C is a constant, okay, C is a constant. And then you have the interval size, okay. You have the label, starting from 0, okay. You go into the ODE, and then your Y minus 1 is the last point. Take the last point. Your last point you assign to this one, okay. And then we actually take the last point to my G. So G will be stored value. G will be stored value, okay. And Y, how about Y? Y here you have the bulb is taking taking the bulb value is only 1 point, okay, and you calculate that and you put it into your Y, and your Y is what? Your Y, let me see, your Y. Okay, your TS is your time domain signal, okay. And time domain signal, we based on, we had that. So eventually you are keeping plotting the time domain symbol and the G, okay. G is your eventual value. And level 0 is the previous point's location label, okay. And why this one take minus 1? Let me see. Let me search for different y. Okay. Okay, y is only one element, so I'm not sure why this one has a minus 1. Okay, I'll check it later. I'll check it later. Anyway, this one is a dynamic system. Okay, let me go back to some fundamental part. Okay, let's go back to some fundamental part. Okay, let me go back to this one. First thing, let's actually go back to some calculus. So some calculus. So let's learn some calculus. Some calculus tell us calculus, okay, py. So now let's actually have a function, okay, have a function. Let's assume that we actually have, let's actually do import, okay, num_p as np, okay. And let's import, okay, matplotlib as print, okay. Let's see, it actually is matplotlib.pyplot, okay. We call it print. These two things, we get it done. Now, next one, what we want to do is time. Time would be, let's do np, the linear space. Okay, this is the time domain signal, starting from 0 to 10 seconds, and then it would totally be 10 seconds, so we use 101, okay, 1001. So let's have every 100 second a point, right? That's my key. So now I'm going to define some function. Okay, this function is take a function of, let's do this one. Let's actually have a function. So let's do this. Okay, let's actually have a x function. X function is using a simple idea. So let's do num_p, the sine function. Okay, sine of the certain tx. Okay, and for tx et. Okay. So we actually have a time, and then we calculate the sine wave. Let's do plotting for this region, okay. Okay, we are done with this one. We save. Now we do plot, okay, the tx, and let's use blue, okay. So the pie plot, okay, pre-plot. So we show the x function in blue color, okay. Okay, so that's the sine function. Now we want to find its differential term, so we can do define, okay, dy dt, okay. So dy dt function will get a function, okay, and an h, okay. And this one is to calculate what? Your dy dt, okay. So you have h. So basically your dy dt will be equals your what, delta f of t plus delta t minus delta, I'm sorry. Okay, I'm sorry. This this f of delta f of t divided by t plus delta t minus t. Okay, so this cancels out. So h, let's assume h is the delta t. It will be something like this. Okay. So you are going to do this, but we try to take this h to be as small as possible, okay, as small as possible, then we should be able to get its derivative, okay? We should be able to get its derivative. So what we will do is actually here we have a certain h, okay? We should also have a certain x value. So that's h, don't call this one x, let's call this one y, okay? Don't call it x because x can be used as our variable. Okay, so let's actually change it to y, okay. Okay, we change to y. Okay, we change to y, and here we do pass, okay. Okay, now we are going to, we need to put the x in there, okay. So here we do have, we want to actually return what? We want to return, okay. So we should have this fp, okay, f prime should be equals the division of these, okay. This is f of the x plus h minus f of the s, okay. We get this one, and that's f prime, and we return f prime, okay. We return f prime. So the point must be enough. That's actually 81003. Okay, that's 81003. So based on that, we actually get the y. Okay, we get a y. So now we actually would do what? We would do. Let's assume that here we have the delta t. Okay, so let's do dt equals 1 e. Let's see. Okay, here we have so many, right? Here we have so many points. So each point is actually what? This much. Okay. So here let's see. Here let's actually don't do this. Let's use the number of the point. Okay, point. Okay, so the points that are assigned to be 10,000 data point. Okay, so the h, what we would actually the dt data t. Delta t we will have will be 1 divided by this. That's my delta t. Okay. So this one, the sample point will be points plus 1. Okay, plus 1. Now we do use point plus 1 to calculate it, and the dt is this much. And then we should be able to get what? Get our dy dt equals this. We have the so-called dy dt function. So this one don't call it dy dt, let's call it y prime. So y prime will be dy dt of the y function with the x value. X value is some xy, okay, certain y value. Okay, let's use x value. Okay, let's use x value. So the x value and a certain this dt difference, okay, and then for x in t, okay, in t is the time, okay, okay. Y is the sine function. Y is actually the sine function. Okay, let's see. No, y is the sequence. Okay, y is the sequence. No, I'm sorry. So here we should have the we should get the data from y, not from t. From y. Okay, so here we should get data from y. So the x in y. Okay, so this function should be num_p that sine. Okay, that's sine. Num_p the sine. That's the function name called num_p the sine. So we pass the num_p the sine into there, and we have the x is the y value. So y value, y is the no. Y value, y, okay, I'm sorry. This one should be time domain should be t, okay, should be t. So we actually change t, and we have sine value, and we have a function, okay. That's good. But y is my original function, okay. This one's good. So this one we set up the t is the sequence, so t is over here. A certain point is x. So the point x here, we have the sine x, and we want to do d sine dt. Okay. And if function sine function being passed to there, you calculate it, you would get the differential part, okay, that's your yp. So now let's actually copy this one. Okay, here let's plot yp, yp in green color, okay. Okay, so let's see. Actually, sine functions, sine function derivative is cosine. Okay, so it becomes cosine. So as you can see right here, it is numerically operated correctly. Okay, and you can see that you actually take differential sine, cosine, minus sine, minus cosine. Okay, so d sine, you will get cosine, because sine you crossing zero, the slope is largest. Slope will make top on here, so actually the differential is 90 degrees, the slope will drop to zero. Okay, so that actually is a cosine. So as you can see right here, sine's derivative is cosine, cosine derivative minus sine. Okay, something like that. Integral is the opposite way. Okay, integral is the opposite way. Okay, so this one is the differential. Okay, let's don't call it a dy dt. Let's call it the derivative. Okay, derivatives. Okay, this one can calculate the derivative. This one can calculate the derivative. Now this one, so we have the source function like this. Okay, we had a function cosine function, and we have the so basically it is a sine function. Function is a sine function. Okay, and then your time domain is t. Okay, so t and sine, these two things we can do derivative. Okay. Now let's try to find integral. Okay, integral. So integral, let's assume that we have a function of integral of f of x dx. Okay, to t. Okay, and it will be your integral of so f t. Okay, let's call it big ft as an integral for it. Okay. So in here, each one of them, okay, each one of them. So there's from you a small chunk of the h, okay. You would do f of what? F of the certain time t, okay, times h, okay. You get original data plus f of t, okay. This thing you get f of t plus delta t. Okay, so you try to do it many times, and you will get the integral. Okay. Okay, so that's what we want to do. So now, let's assume that we have 101 point. Okay, and the first one is your f0. Okay, your big f0. You got a big f0. Okay, You got a bit F0, and based on your bit F0, you will try to get your next value. Okay, you'll try to get your next value. So totally 101 point. If you do every integral, you should totally run 102 time, 101 time, and get each value. Okay, and you should get one actually from the F0. You don't need to do it. Okay, and then the other you totally go 100 point. Okay, so let's actually try to use the integral function that we have it a moment ago. Okay. So we still would use the sine function, and here we will use y integral. Okay, we are going to do y integral. Okay. Let's see. Let's actually try. Okay. Psi p inter or int sine function. Okay, let's actually try to do this one. Using numerical method here. Okay, let's do this one. This one, ds dy. Okay, so here we have this differential equation. So dy dt equals x minus y. Okay, we got this one. So that's the dy dt. So we try to sum the equation. So we need to put the differential equation here. That's the one we try to sum. And y0 we know, and t is x. Okay. So you need to define a different function. So here we try to sum y. So our equation should be df function dt need to be equals sine t, right? So that's our differential equation. So our df dt should be equal to sine function, right? So that one we should be our df dt, we know. So put the NP sign, no problem. This one, no problem. Now, next one is the X domain. This one, okay, so 100 point. Okay. Oh, your y and your let me see. Okay. So your dy dt x minus y. Okay. Your y and x, you have the xs. Okay. So you now let's try this way. Okay. So here let's actually go back to this the test one. Okay. So right here let's do function. Okay. d sine dt. Okay, so we would have a function okay, and we also have this one the x we pass in. Okay, so let's see. So this one should be returned. Okay, f of x. Okay, sine function you return the this dy dt is a sine function, right? Your function, let's see. The dy dt, okay, equals y and x. You have only one thing, so that's actually y minus this, okay? In our case, we do have this one, okay? And okay, we have f, okay? Okay, so this one is like that. So we go here, so we need our, this one, we should have this one for d sine dt, okay? And we 0 to t, and this one should be public arguments with the np, the sine, and the what? We need to pass a variable. Okay, this variable is the arguments. Let's put the t there. Okay. Okay, still wrong. Let me go back. Okay. So this one is actually XS. XS is a time series. Okay. And you don't have an argument. So let's see. Let's don't put argument for it. Okay. So that's a T, the time sequence that we provide. Okay. Let's don't put that. Okay. It's not callable. It's not callable. So let's do arguments. Okay, equals beta sign. Okay. Okay, so this one beta sign still not okay. So there are two variables you need to have, and you want to create that. You need to pass something to it. Okay. So there's a time sequence. So let's look at this one more carefully. This one is sine integral. Okay, let's just copy this guy. Okay, just copy this guy to my test program. Let's create a test 2. Copy this guy to test 2. Okay, we have the SY. So we need to run, okay, import numpy as np, okay. So we get that point, we have the Y, not right now we know ODE. Now the Y is what? Y is what? We did get a Y, right? We didn't get a Y. So this Y is, we don't get a Y, right? Right here we have Y naught, we have the time. So this one we can change it to time. Change it to time. So we have a time, we have a Y. This equation is differential equation. So we do define this differential equation. We do define dy dt equals y minus t. Okay, so that's actually okay. That actually is an x. Okay, that's actually an x. Okay, so t is a sequence. That's okay. So x is each individual point. So this value actually is it will be separated by separated by t. So we don't need to worry about it. The y function is the problem we want to solve. Okay, so that's something we don't need to worry. So let's actually do this one. Okay, so that's one call. Okay, I'm sorry. Let's actually do figure. Okay, let's do figure show. Okay, right here we do plot. Okay, ys HT and ys. Okay, and let's put it as red. Okay, so right here we do need to run pilot import and start. Okay, so let's do this one. Let's save. That's wrong. Okay, so we got it this way. We got it. Now let's actually modify it a little bit. Okay, the flatten we don't care. Okay, the flatten we don't care. Here we do have y. Y is some function. Okay, so let's actually drop y. Okay, y is the target to be integrated. Okay, so y is the target to be integrated. So we have this y, and we need to wait. This one is y. So right here, y is the function to be integrated. Okay, and y naught is 1. So here we have the x. So let's try this one. Don't do this. Let's do NumPy, the sine function. Okay. Even the whatever x given, we directly return this. And that guy, yeah, we do got it. Okay, we do got it. So now let's solve our problem. Okay, to use the ODE, we need that. So let's go back. Okay, this one is okay. Let's get this one. Go back to my calculus. Okay, now sorry for that. So here we do need to have, we don't need an integral. We put it over here. Okay. So this one, let's call this guy is actually sine dy dt. So dy dt is the sine function. Okay. Dy dt is a sine function. So here we do dy dt. Okay. So it's dy dt. Okay. So that change the name to dy dt. Okay. And y actually is a dummy variable that you don't need to care. Okay. That's the integral function. We don't need to care about it. So here we do have this integral and t. Okay, and we insert f dot to it. So that's not a problem. Let's save. Okay, and let's run it. Okay, sorry. Insert. Okay, insert. It cannot be insert. This one is array, maybe array. Okay. So let's do this one. Let's do while I equals list of yi. Okay, then we can insert it. It come back maybe an array. Okay, don't worry. Okay, the dimension is different. So let's don't even do it. Okay, do not need to insert. Okay, we got it now. Okay, we got it now. Sorry for the delay. Okay, this one we are using ODE to solve it. So basically, you need to set up your differential equation, initial value, and your time sequence to solve it. Okay, I'm sorry that actually I did not use this for a while. So that one is when you do integral, time domain integral, you can use that. Okay, so this integral function will study later. Okay. Okay, this one is using the ODE to solve the equation to do integral. Okay. Now let's actually use our own brute force way to do integral. Okay, so let's use our own brute force way to do integral. So let me actually again use this one called integral f function. Okay, we need to have the f not okay initial value. Okay, and then the time series. Okay, time series. We try to do this. Okay, so we would have a g value that actually has the initial value of n0. Okay, that's what we have. Okay, the time sequence we have always cited. So that's actually for I. Okay, in the range of the length of the t. Okay, so we get every single one of them, and then we need to do f1. Okay, f1 would be equals f0 plus the t. F actually is the value. Okay, so here you should use the t's i's value times theta t times delta t times the t of I plus 1 minus t's i's value. So here you actually do every single one. You got f1, and then you insert g that append. Okay, your F1 to there, and you eventually return your G. Okay, this is our own way to do integral F initial value and the time sequence. So let's copy this integral over. Okay, so here we have this one. Okay, my own version of integral. So here it will be numpy dot sign. Okay, and this one is yi2. Okay, yi2 equals this one. So let's do this. Let's actually do this one. Okay, let's do f and axis. Okay, equals this one. Subplot. Okay, and subplot. And then here we have 4 and 1, 4 row and this. Okay. So this one we would have ax 0 per this one, ax 1 per this one. Okay. ax 2 per this one. Okay. ax 3. Okay. yi2. Okay. And let's do it. Okay. Let's actually get these. Okay. Get these and save all. And let's go. Okay. Outer bound. Outer bound. Wait. Okay, that's actually 101 is outer bound. 101 is here that's actually 2 minus 1. Okay, sorry for that. So set all. Okay. Okay, we got them. So here let's see. We got a sine. Let's see. This one is not sine wave. Okay. Our F naught actually is minus cosine 0. Okay. We have a sine minus cosine 0 as the initial point. Okay, we do integral of the sine function. So we do integral of the sine function. So we do have this is positive. So the integral value we get the not what we want. Okay, there's a difference. So every single one of them we are delta I. This one I think is okay. F of ti is your sine function. Okay, we are trying to calculate the integral of sine function. So integral of sine function initial value is minus 1. So that's actually 2 minus 1, starting from minus 1. Okay, so we start from minus 1. We have sine value, and sine value is t of this one. So this whole thing should be positive. It should be moving up. It should be moving up. It is moving up, but it's not behaving like the sine function, the integral of sine function. Okay, so we get that. Oh, okay, I forget to modify it. Okay, and then my f0 need to be f1. Okay, so that will continue to integral. Okay, so let's save one more time. Okay, sorry for that. Okay, this is my main integral function. Okay, now it's the same. Okay, now y and y2 are actually same. So this way is the manual design for integral. Okay, manual design for integral. We do cover this one for derivative, manual design for integral, and the ODE. Let's actually move this guy to be with the ODE. Okay, to be with the ODE. So this one is dy dt show equation. Okay, for ODE. Okay, for ODE. We do ODE. Okay. This one is custom design. Okay. Interval. Okay, this one is custom design interval. So over here, well, because of the dynamic system, we try to give you the man-made, homemade derivative and homemade integral function. Okay. And then try to solve it. Okay, so these are the basis for doing the dynamic system. Okay, so doing the dynamic system. And let's go back. Let's go back to our dynamic system. Okay, this one let me close. Okay, so basically that's the water function. Okay, we can use design the differential equation and then put into the ODE solver. Okay, and you can also use your own version to do it. Okay, you can also use your own version to it. You can assign a line width to make it wider. Okay, and the line styles to be solid or to be dashed. Okay, and you can solve the equation by ODE. So ODE is model. Remember, this model should be put in what kind of format? You should use the dy dt equals something. So you need to design the dy dt function. And there are some parameters you can put it later, but here initial value and time sequence need to be provided. Okay. Okay, that's the key point of using this SciP that integrate. Okay. And if you don't like that, you can use my own brute force way to do calculation. Okay. Sorry for using too much time for it. Okay, so anyway, I give you some sort of introduction for this different equation. Okay. Okay, that's the time sequence derivative. So far we have what open system for it. Okay. Now we look into the balance of equation. So the balance of equation is you will have the mass conservation, or you will have the four kind of conservation. Okay, and you set up your equation. And you set up your equation, then you can based on that to solve your ODE or PDE. Okay, then you find the proper way to do it. But so far, the ODE or the PDE, they are both in time domain. Okay, they are both in time domain. So those kind of equation you can set up and try to solve it. Okay. So right here, we don't go into the detail of how to solve it. You can actually refer to the last year's talk about it. Okay. My job this year is to show you how to use this different function. Okay. And the model can be very complicated. So we don't go into those details. Linearization of the differential equation, you set up an equation like this, and you can actually do linearization of the differential equation, partial derivative, or whatever. This one you can look into it. Okay. Some of the integral you can try to find its symbolic solution by using some SciP. Okay, by using SciP, it actually is okay. You can use the SciP to find it. Okay, and you can also find a numerical solution. Okay. And here is to solve it and then put it into 3D domain to see the tangent plane. Okay. To see the tangent plane. Okay. Okay, anyway, today I would like to stop over here, okay, because I don't intend to go to these different deep functions, okay, just cover some basic integral. So if you are interested in the control theory of this deeper Laplace transform, you can look into my last year's video and may also download the sample code to run it, okay? And sorry for the delay in finding the ODE function, okay? See you next time. Bye-bye.